Again, this week is basically an introduction, so we'll skim through the first set of slides, and hopefully if we're done, we can move on to the next set of slides. So both the first and second chapter slides are up on the website right now. So we'll move on. Please go through the syllabus in more detail. So I think we skimmed through the material that we have that we will be covering in class last time quickly. Basic idea is we will have 2 exams and a final. That's from a grading policy perspective. And I think we went through the main topics. And today we will sort of, again, the first set of slides also goes to the main topics that we will cover in the class again. So we'll go through this quickly and hopefully get started on the second chapter. So the first chapter is basically an introduction, a lot of terminology, right? So power systems is really like we saw last time. And if you're not here last time, the video is on the website, so you can watch it. But like we saw last time, the objective is to reduce these terminologies that we're going to talk about to a simple circuit. At the end of the day, it's nothing but a simple electrical AC circuit analysis similar to what you did in 214. That's the objective of the course, to show you how to reduce the big power system into an AC circuit analysis problem like 214. So there will be a lot of terminology involved, and a lot of this course is about you understanding the terminology, really. But I think the math and the circuits behind it is something you already know. So hopefully it should be not too bad. Okay, so an electric power system contains, well, we talked about the elements contained in an electrical power system. So we have groups of power stations, groups of transformers, switchgear. Switchgear is a term we refer to, for example, bus bars, the nodes in a power system. Nodes in a power system are nothing but, like an electrical circuit, you would bring 2 wires and connect them to each other, and that's a node. In 214, you're calling that a node, right? A similar thing. So you have a generator, and you have a load. You want to connect them with a transmission line. This transmission line will be connected to the generator. How will it be connected to the generator? At a node. This node we call a bus bar. This bus bar is nothing but, some pieces of copper. So as the word means, a bar that we call a bus in the system. So it's, if it's a 3-phase system, and typically all systems that we deal with will be 3-phase, there will be 3 bars in the substation. So the bus bar structure and the measurement equipment, so you will have to be measuring the currents and the voltages associated with this bus bar, and the protection devices that go along with that, and which includes, for example, the protection devices that give the control signal, as well as the protection devices that actually do the physical opening and closing of the circuit, right? So there will be a brain, for example, that will interface with a sensor. The sensor will measure currents and voltages. If the currents and voltages are too high or too low, what do you want to do? You want to disconnect because the house burned down, because there's a fault somewhere, because there's lightning somewhere. All of these are different types of faults. So you will measure them. Something will process, which is called a relay in a power system, and then then you have to open up the circuit or close the circuit back again. Correct? So all of these together are what we refer to as switchgear. Right? So it's just a fancy word for all of these things grouped together. So besides, power stations, transformers, and switchgear, which are interconnected by overhead lines or underground cables, we have loads in the power system. So, of course, you have to operate within limits. So, for example, every voltage level. So we talked about the different voltage levels that the power system operates at. So we said that we typically increase the voltage after generation so we can transmit power with lower losses, right? If you increase the voltage, your I squared R losses are lower for the same amount of power, right? P equals V times I, high V, low I, so I squared R's losses are low, right? So we typically increase the voltage. And we said that big consumers, bulk consumers of power, will typically tap into the power system at higher voltages. Here we are tapping into the power system in this building, in this building downstairs in the parking lot, we have an 11 kilovolt to 480 volt transformer. This 11 kilovolt to 480 volt transformer belongs to Kahrama, right? So, or actually, in this case, it actually belongs to Education City. Education City taps into Kahrama at 11 kilovolts. So then they distribute within Education City at 11 kilovolts. So everything coming in at 11 kilovolts, that is Kahrama giving Education City power. Then there's a transformer within Education City to take this 11 kilovolt and transfer it to 480 volt. Step it down to 480 volt, and then 480 volt is the line-to-line voltage. So if you're talking about single-phase voltage, line to neutral voltage is the 480 volt divided by square root of 3. And we will review three-phase for those who need a refresher in three-phase. So we will do that as well. So you have to, this voltage has to be within certain limits, right? If you're operating a piece of equipment that's 400 watts, this 400 watts is at a specific voltage, and hence a specific current will flow, right? Right? It's if you're fixing the voltage, the current will be. I mean, if you say this laptop operates at 15 volts, and it requires 15 watts of power, that means I'm drawing 1 amp, right? But if I bring the voltage down to 7.5 volts, assuming this laptop works, how much current am I drawing? I brought the voltage down that this laptop is operating at from 15 to 7.5, but I'm still consuming 15 watts of power. So what is the current I'm drawing in this case? Huh? Double to 2 amps, right? So do you think this is designed to carry double the current versus the rated operating conditions? We don't know, right? I don't think it is, right? But I personally don't think it is. But without looking at the design, I don't know. But higher current means higher losses, right? Higher losses means what? More heat, right? Higher losses means more heat. And then they're making these laptops very thin, low profile, etc., etc. So they want to do it without cooling. They want to do it without any fans and noise and low profile, etc. So do you think they will accept a higher power loss? Probably not. So they designed this within a certain region, limits, right? So every piece of equipment is designed to have operating limits of voltage. After that, it will disconnect or not operate properly, or you will burn it down. If it doesn't have the proper protection, it will probably burn down. If it's protected properly, then it will disconnect itself. It will say, I cannot operate now, the voltage is too low, right? So, and there are limits at the different voltage levels that differ at every voltage level versus the other. So at the distribution level, it may be 5 or 10%. At the distribution level is probably the strictest, because these are low voltage pieces of equipment that need to operate within very, very small ranges. Yeah. But if you're talking about at the 200 kilovolt level, things may be a little more lenient, because you're not going to be tapping into the 200 kilovolt level as a consumer, right? The person tapping into 200 kilovolt level is either a bulk consumer like, Ras Laffan City, that has their own set of power engineers and they are monitoring and seeing what's happening in real time. That's not us. We're just connecting here and we operate and we hope it works, right? And if these light bulbs keep blowing up at home, it's okay. We go and change them and we don't have an issue with that, right? And that's a problem, right? It's caused because of the poor power quality. So the standards differ at every voltage level. So at the distribution level, it may be plus minus 6% is what's allowed, and frequency may be allowed to deviate from 50 hertz plus minus 0.5, but have an average of 50 hertz throughout the day. I went and visited the control center, the distribution control center for Kahrama, and I will show you a video about the distribution control center, a utility control center, and the engineers are there sitting, and the frequency, they have a big screen there displaying frequency. It's a big concern, because what's happening is you want to make sure that it's maintained. And then why would frequency change in a power system? Think of the generator, how a generator works. Sure, if the speed changes, but why would the speed change of the generator? So typically, how does a generator work, right? You have a prime mover running the rotor, right? this rotor has the field winding on it, which if you rotate it, so it's a field winding that you're supplying, and it's creating an electromagnet, right? That has a certain orientation. But if you spin that, that means you're creating a time-varying magnetic field in the air gap. This time-varying magnetic field is linking the coils in the air gap and hence producing voltage at the terminals of the generator. Then you connect an electrical circuit. If you connect an electrical circuit, what will happen in the coils of the stator? Current will start flowing, right? If you have if there's voltage and then you connect a circuit to the terminals of the generator, current will start flowing. If current starts flowing, there is a reaction that's going to happen on the generator, right? If you have a piece of conductor with current flowing in a time-varying magnetic field, what is developed on that conductor? No, no, force.
Okay, yes.
Remember, if you have current flowing already in the conductor,
Then, okay.
and you're moving that in a time-varying magnetic field, force will develop. But if you don't have current flowing, which is the initial thing what we had was a turn that we are rotating in a magnetic field. That turn, what happened was, because the turn was rotating in a magnetic field, you had the E equals n d phi by dt developed across it, right? n d phi by dt is what? The rotating magnetic field. The d phi by dt is the rotating magnetic field, the time-varying magnetic field. So if you have a time-varying magnetic field and you put a piece of wire in a time-varying magnetic field, then voltage will develop. If voltage develops and you close the loop with a load, right, then current will flow. If current flows, then you have force. And that force will be opposing that prime mover force that was put in. And that's why things are balanced, right? If there is no force developed, then if you spin the prime mover, and theoretically there's no losses, for example, what will happen? It will keep spinning forever. It will keep spinning forever and it will not change speed at all, right? But what's happening in generators, and luckily this is what's happening with generators, is as soon as you spin it and you create this time-varying magnetic field and you create the voltage and you create the corresponding current, a force is developed to oppose the input force. So then we have a steady state condition. The force coming in is equal to the force coming out plus the losses. Right? That's steady state. Right? If there's only force coming in and nothing going out, is that steady state? What that will do is keep accelerating the rotor. If you keep putting a torque, if you have a torque applied and there's no load and there's no losses, what will happen? You will keep accelerating. Right? It's like riding a bicycle down a mountain. Right? You're the torque or the load that you're applied to the bicycle. Right? If there's nothing resisting that, if you don't have brakes, it's a problem. Right? So you will crash into the wall. So, and that's exactly how the generator operates, right? So the generator requires you to have this force that will make it operate in steady state, right? And then if you need, so now what happens? So if you draw more power, what happens? If you draw more power, if the load is drawing more power, that means there's higher force on the generator rotor. That's going to slow it down, right? For you to bring it back to steady state, if you slow it down, that means the frequency is going down, right? The frequency of the generator output is equal to, is proportional to speed, right? There's the back EMF. The back EMF generated by a machine, or the voltage, this E that's generated by the machine, depends on the frequency of the rotor, right? So if you rotate the rotor one time, you will have voltage that is one full period, one full cycle. Rotate it fast, this one full cycle will happen in a shorter period of time. Rotate faster, shorter period of time, right? So it's directly proportional. The output voltage is directly proportional to the speed. So now if I keep loading, this electrical circuit keeps drawing more and more current, which requires more and more force on the windings, then what will happen? It's going to slow down. If it slows down, it deviates from the 50 hertz, right? So what do? You open up the steam valves and increase the torque or force coming in, right? So So that's why this is an important consideration. It's an important consideration in controlling generators. So one of the important things that you do when you control generators is control its speed. And it's done using a governor control circuit. We will talk a little bit about that later. So it's a speed governor. What else is important in a generator? So the frequency and the value of the voltage, right? How do you control the value of the voltage that's coming out? How was this voltage generated? It was generated by, you had the stern that was rotating in a fixed magnetic field, or the stern was stationary and the magnetic field was rotating, right? But if this magnetic field is fixed, the E that's generated is fixed. And that's why you have a field winding control circuit. The field winding control circuit, what does it do? It controls the value of the magnetic field that's generated. So if you control the value of the magnetic field that's generated, then you can control the value of the voltage, right? So now you have control over the voltage and frequency. And that's how you control the generator, right? And it's actually a blessing that this physics happens, because if when the generator slows down, it's because it's loaded. If it slows down because it's loaded, then what's going to happen? Another generator that's not loaded will pick up the rest of the load. It's like for example, you have a few people running and holding a stick, right? And then they are all pulling a big load behind, right? If somebody is faster than the other, that person is what? Is more loaded, because again, the load is connected to the stick, and 3-4 guys or ladies or are pushing this stick forward, and the person that's faster is probably putting more load than the rest, right? So what happens? He gets tired, right? And then what happens? The other guys can pick up the slack, right? And they're all moving together. At the end of the day, the speed that they're moving at should be an average of 50 hertz, right? So if he gets tired, the other guys pick up the slack, and they keep going forward. And they keep doing this all the time, right? You can never be all the same. All the generators in the power system are never going to be operating at exactly the same frequency, right? So they're always doing this. There's always a deviation in power angle, is what we call it. Okay, so it's always an average of 50 hertz, assuming that they don't fall out of synchronism, right? So what happens if one of these people pushing the stick slips? He cannot. The guys are so much faster than one of them, and or the person at the beginning got very tired and he just fell down because he kept going forward faster and faster and faster and faster, and what? And then there's nobody moving forward anymore, right? So people will fall down, right? So that's the generator falling out of synchronism. So when you keep loading one generator, when you keep loading a generator, what happens is, at some point, again, there are two generators operating together. They both have an average of 50 hertz, so they're both spinning at 50 hertz, right? So if you're sitting on one of the rotors, how do you see the other rotor? You took relativity, right? Right. So if there are two rotors, right, and there are two rotors spinning at an average frequency of 50 hertz, you will see the other rotor as if it's stationary with respect to you, right? But there may be some angle deviation. If it's loaded more than you, right, it will be slower. It will lag a little bit. If you're less loaded, then you'll be faster, right? So you will see some relative motion in that case if one is loaded versus the other end, right? So what was I saying guys?
Why does it always have to be 50 hertz? Why 50?
Why 50? Oh, because people decided. No, it's interesting. So you cannot have DC, right? DC is not good because of what? What's the benefit of AC, first of all? Huh? We talked about this last time, huh? Power transmission. It's the benefit of AC is because we have a transformer. Because AC quantities can be stepped up or stepped down with a transformer, and we need transformers to be able to control losses when we are transmitting power longer distance, right? So if people had power electronics, when electrical power was first invented, maybe things would be different, right? Because there was no power electronics back then. With power electronics, I can take any quantity and convert it to any other quantity. I can take low voltage and step it up to thousands of volts, right? And in that case, I can transmit, and then I can step it down at the load, and I have no problem, right? That's with power electronics, you can do that. But there was no power electronics back then. So at that point, people, there was Westinghouse and GE were two companies. One was promoting AC power systems, one was promoting DC power systems. Who won? The AC power system won back then because of the transformer. When the transformer was invented, the AC system won. And then, okay, AC. What frequency is your question, right? Or what frequency is your question? Yeah. So I think it's an optimization process, right? So we will learn later when we talk about transformers that the size of the transformer is sort of proportional to the frequency. So if I increase the frequency, people that took power electronics last semester, you built a transformer, right? Yes, you built a transformer. That transformer was operating at what frequency? Huh? What? 10 kilohertz or 12 kilohertz. I don't remember what exact frequency Mu'in selected, but it was a very high frequency, right? So, and that transformer was pushing about half a kilowatt, so 500 watts maybe through it, right? And it was this small. If I tell you go buy me a 50 hertz 500 watt transformer, it will be this big, right? So the size of the transformer is directly proportional to its frequency. Okay, so at the same time, you cannot choose very high frequencies because there are certain things. For example, motors, an induction motor. It's the speed of an induction motor is equal to what? NS is equal to what? Who took 338? 120 F over 2P, right? 120 times the frequency over the number of pair of poles, right? So if I have a 10 kilohertz frequency, the speed of induction motors that you just plug, the fridge, the air conditioner, the lathe in the workshop, the blower, and all of these devices, right? You want to operate them at useful speeds, right? So the useful speeds are certain speeds that they're not. The useful speed is not 10,000 RPM for a motor that runs the air conditioner compressor, for example, or something like that, right? So if I chose a very high frequency, then I will have all the devices that I'm going to be plugging into the utility have to operate at that frequency. So induction motor operating at 10,000 hertz has a rotor speed of what? 120 times 10,000 over number of pair of poles. So divided by 4. So you're still talking about maybe 100,000 RPM or something like that, right? So you won't be. So there was an optimization process, right? That can be one reason, yeah. And that's why, for example, here versus the US, the US operates at 60 hertz. Why? Saudi Arabia has parts 60 hertz, parts 50 hertz. Right? So it's airplanes operate at 400 hertz. If you can go work for Qatar Airways, for example, the electrical power system in an airplane is a 400 hertz system. Why?
400 hertz is better for deviation.
Size. So they wanted to reduce size and weight. It's important to reduce size and weight in an airplane, right? At the same time, you still want useful devices that can operate in certain speed ranges without adding additional electronics, right? So it's an optimization. So and they found, and maybe if you do the optimization process, you will find that maybe beyond 500 or 1 kilohertz, that the benefit you gain in size is not too much anymore, right? Versus the amount of complexity that you have to add in the electronics, right? So airplane power systems operate at 400 hertz mainly because of weight.
So as the frequency increases, the size decreases?
The size of all reactive elements decreases with frequency. So capacitors, inductors, transformers, these are all the reactive elements that we have. Motors. all of these, all the size of anything with a reactive component, meaning L or C model in its model, right? Transformer has an L in its model. Motor has an L in its model. Anything with an L or a C in its equivalent circuit model will reduce in size with frequency, and we will look at that later. So that's the 50 hertz thing, okay? Again, transmission is typically, again, I've heard, I think now there is a transmission system that is higher than 765 kilovolts. In China, they introduced a 1 megavolt DC transmission system, actually. So they keep going higher and higher, right? And China is a very good example of a place that they can do that. Because what people found is when you increase the voltage and use DC transmission, it's very good to, it's a lot more efficient than AC transmission for long distances. So in Qatar, I think the longest transmission line we have is like 80 kilometers, right? So it's a very different scale than China, right? So DC transmission in Qatar maybe not very useful yet. It's used, for example, in subsea. So some of the subsea connections between the industrial facilities onshore in Ras Laffan and the offshore rigs, for example, offshore platforms, these are sometimes are DC. A lot of them are DC. But besides that, in Qatar it's AC. There is a connection between Qatar and Saudi Arabia that is DC. So Qatar operates at 50 hertz, Saudi Arabia operates at 60 hertz predominantly, right? So how do you connect these two? You know, the Gulf is all connected now, right? The GCC grid is all connected. So Qatar is connected to Saudi Arabia through a DC connection, DC interconnection. So we have 50 hertz, certain voltage, specific frequency. We don't have to. If I'm going to convert this AC to DC, and then take this DC, convert it back to AC using power electronics, then Qatar and Saudi Arabia don't have to worry about the generators being synchronized or out of sync, or the stability on this side or stability on this side, right? They operate separate grids, for example. But they can exchange power through this DC link, right? So the structure of that DC link is something we studied in 438, for example. Yeah. So it's a way to transfer power between systems. So instead of a transformer, it's like a transformer. So you can think of it as a DC transformer, right? At the end of the day, a transformer is allowing you to connect two systems with different voltages, right? So, but they have to be the same frequency in the case of a transformer. If you use power electronics, you connect two systems, but they can be different voltages and different frequencies, right? Or they can be similar frequencies, but they're not synchronized, right? So for a generator to be connected into a power system, into the same power system, again, we said that all the generators that we have are like, runners holding this pole and running together, right? They have to be running at the same average speed, right? If one is not running at the same average speed, that person is going to fall out of sync and is not going to be connected to the system. This is exactly how the power system runs, how the generators in the power system run. Here we have some representative voltages of residential voltage levels, commercial consumer levels, and then industrial consumer levels. Ras Laffan, I know RasGas, for example, connects at 132 kilovolt to Kahraman. Different consumers will take voltage at different levels. We talked briefly about that last time. We touched upon AC versus DC. Besides transformers, yes, one good thing here is circuit breakers, right? So we talked about the benefit of transformers in AC, right? And the fact that we can step up and step down. Another very important consideration is, when you have a problem in a part of the system, you want to disconnect that part, right? And you disconnect that with a circuit breaker. Circuit breaker is nothing but two contacts, right? Two contacts, they open up, and you disconnect the circuit. So it's a lot easier to disconnect AC voltages and currents. Why is that? Because these quantities are always going through zero. So there are points when the current is zero, always. So circuit breakers like that, because if you disconnect at a point where the current is zero, then the arcing is very low, right? Arcing is developed because of what?
Breaking the air.
Not breaking the air, breaking what? Arcing, okay, so you have You have a circuit breaker, it's a switch, right? Circuit breaker is a switch. And you have a generator here, for example, and you have a power system. A power system, what do you think is the power factor of the power system? Is it unity? If it's unity, it means all we have in the power system are advanced power electronic converters that are maintaining unity power factor, and resistive lighting, which is the incandescent lighting, not the fluorescent or the energy efficient lighting, and maybe some resistive heaters, and what else is resistive? Pretty much, that's it, right? So this is what's the major? What do you think are the majority of loads in a power system? Huh? What? No, lighting? No. Why? Due to what? I mean, industry consumes probably quite a bit of reactive power. So all these motors have magnetic fields. Magnetic fields are set up using the reactive component of power, and we will talk more about that. So I can model this. I can model the load in the system as a big inductor. This is like the big power system, right? For example. So if this is a big power system and it's a big inductor, inductors don't allow abrupt changes in current, right? So VL is equal to L di by dt. IL is equal to what? 1 over L integral of VL dt, correct? Plus an initial condition. So this is current through an inductor. Current through an inductor is the integration of the voltage, right? So when you're integrating, what you're doing is adding areas together. So you have an area, and then you have another area, you have another area, and you add that together. So what inductors are doing are accumulating. Basically, inductor current is an accumulation of the shape of the voltage, right? So inductors don't allow current to change abruptly, right? And if current changes quickly, meaning this delta T is small, right? Delta I over delta T. If this delta T is very small and current changes abruptly, meaning I open this switch and the power system was consuming full load, what happens?
It's like an open circuit.
Sure, that's what you're creating, an open circuit. But what happens during this open circuit? You change. This was a big change, right? It was consuming full power, and then you made this what? 0. You opened it up, right? And it did this in a very short period of time, right? So if it does this in a short period of time, what is this quantity going to be? Huge. Which means the voltage across the inductor is going to be huge. Assuming the source voltage is low. So let's ignore it. For Kirchhoff voltage law, ignore it. Ignore the source voltage for now. This is a huge voltage, right? This is an open circuit. What is the voltage across this open circuit? The same as this inductor voltage, right? So it's a huge voltage, right? So last class we said that the breakdown voltage of air is 30 kilovolts per centimeter, right? So if you have two contacts that are 1 centimeter apart, and you have voltage across them that's 30 kilovolts, you break down the air and you cause an arc, right? So if I'm operating a power system at 400 kilovolts, and these contacts were closed, now you're going to open them. They're a lot closer than 1 centimeter, right? So you're opening it up. You will see a huge arc develop because you broke down the air, because the breakdown of the air is 30 kilovolts per centimeter. You were stuck to each other. The contacts were stuck to each other. Now you're opening it up. And you will see a huge arc develop, right? And that's the difference between the different types of circuit breakers. Different types of circuit breakers quench this arc in a different way. So some are air circuit breakers. Some are vacuum circuit breakers. Vacuum is probably better than air, right? A vacuum does not allow the burning process to continue and tries to quench that, right? So air circuit breakers are the cheapest, right? But they're the biggest for the same voltage level. Vacuum circuit breakers, a little bit better. Oil circuit breakers, maybe a little bit better. Gas insulated circuit breakers, so there's a very good gas called an SF6 gas. So gas insulated circuit breakers are the gold standard, but they're very expensive. So if you bring, 50 kilovolt breakers from different technologies, the gas insulated breaker, the GIS breaker, will be the smallest, right? Why? Because it can quench the arc better. That's the only difference between them is the quenching of the arc mechanism. So if it can quench the arc better, then I can make it smaller, right? If it quench the arc quicker, it can make it smaller, right? And then, but it's more expensive. So you use it, for example, if you go to work for RasGas or Qatar Gas or whatever, and you go to the LNG trains that they have. I mean, these are very important loads. They're in a very big industrial facility. There are lots of people. The space is limited in the refinery, etc. So you will find that they will have all gas-insulated circuit breakers. And these are big. So I'll try to get some pictures of these equipment, but they will be, placed in a big room, and they will have the corresponding switchgear inside them as well. So the measurement devices will be inside, as well as the circuit breakers and the bus bars. So the bus bars will be immersed in the gas. The current and voltage measurement devices will be immersed in the gas, and the circuit breakers will be immersed in the gas. It's like a big, I don't know. It's like big cylinders, and you will not really know what it is from outside until you go and see. Okay, it will say GIS on it, or gas insulated switchgear on it. Yeah. Okay, so circuit breakers are another important consideration when you AC versus DC. Also, we talked about the size of motors, right? So if you compare, if I have a single-phase motor, assuming this is my voltage and assuming this is my current, what does the power look like? Instantaneous power. Sinusoidal? Yeah, it's a multiplication. So, but is it going to be sinusoidal? Is instantaneous power going to be sinusoidal? No. You're multiplying these two by each other. It will look something like this, for example. How about if you multiply these two by each other? It will look like this again. Right? So this is power. So power in single phase is pulsating. Right? This has an average value. Does have an average value, right? So you can get some real power out of it, right? And we'll talk about review real power equations later, but it's a pulsating waveform. In three-phase, I'm not going to attempt to draw it. People that took 438, no, I don't draw three-phase. I typically have a piece of paper that has it pre-drawn, and then I delete and cut it. It's too complicated. But in three-phase, it's like having three of those, but phase shifted. So can you imagine, for example, having this one and then another one here, and then maybe another one as well, draw as well here, for example. So it's constant power. So, and we will do the math to prove it, yeah. But yes, power in three-phase is constant, right? So I have pulsating power versus constant power. But what is the value of current in all cases? The same. What's the value of voltage? In all cases, the same. So when you select a conductor and its insulation, do you select it based on power transfer, or you select it based on voltage and current? Voltage and current, right? So you will select if you have two conductors next to each other, then you have to select the insulation to be a certain thickness so that you don't have arcing problems, right? So that's the selection of insulation based on voltage level. And then current capacity, the amount of copper will be dependent on current, because if you have 1 amp, that means I squared R is a certain amount, right? So you will select the conductor amount of copper based on the amount of current that you push through, so that you don't increase the temperature limit too much. That's how you select a conductor, right? So for single phase, I selected conductors that can withstand a certain voltage and current, but I had a low value of average power. Versus I buy a three-phase motor, and wow, it's amazing. For the same power, or for the same conductors that I'm using, for the same insulation and same current carrying capacity, I get a much better, much higher power density, because of this idea of pulsating power in single phase versus DC power or non-pulsating power in three-phase, the non-pulsating nature of power in three-phase systems, right? So Is it clear? So you use the same conductors because you had to push in the same amount of current and insulate the same amount of voltage, right? It's still, you bought a motor that's 240 volts, rated for 2 amps, single phase, and then you bought the same motor, 240 volts, rated for same amount, same value of current. But the 3-phase motor will be a much higher, the rating of it will be higher because of this phenomena, because single-phase power is pulsating. Versus 3-phase power, it's basically like having 3 of those phase shifted with respect to each other. You will get a much higher average value. It's actually constant, yeah, it's actually constant. I didn't draw it nicely, but you will get it, it will be constant. We will look at the equations later and we will see that the terms that have the pulsating component, they cancel out. And you're left with a nice average power. That's 3 times the value of that. You have that's 3 times the value of the average power in single phase. So we will look at that. Yeah. So that's what this slide is trying to say about pulsating power and electric machine size, etc., etc. 3-phase transmission system will carry greater power than a single-phase system as well. Okay, let's talk quickly about 3-phase now. So let's say you have 3 single-phase loads, right? You want to feed these 3 single-phase loads, right? 3 homes. You want to feed all 3 homes. So if I was feeding them from a single-phase supply, I will take this, and these. The power rating of this is equal to the power rating of the load. So I bought a supply equal to the rating of the load. So for me to supply the second home, what do? I have to get another generator, right? Feed this second load. For me to feed the third one, I have to do this. We agree? Okay, so for me to feed these 3 single-phase loads, I needed these 3 single-phase sources, and to transmit the power, I needed 1, 2, 3, 4, 5, 6 cables. Correct? So to transmit the power on single phase, I needed 6 cables. These cables carried a certain value of current, right? This value of current, the current going out here is what's going into this load. Okay, so all the value, assuming the loads are equal, then the currents in all 3 conductors are the same. Okay, so this is what you would have to do if you were going to feed the system using single phase. If I was to transmit power on 3-phase, how would things change? So let's look at this. If I do this, is it acceptable? Right? It's like having 3 batteries. Can you connect the negative terminal if you have 3 batteries in parallel? Right? Can you connect if you have 3 batteries like in parallel? Each battery was feeding a resistive load. Right? Can I connect all of these together here? You can, right? No problem. And you will still, this battery will feed this load, this battery will feed this load, this battery will feed this load, right? And if that's the case, then I can also do this. I can also connect these 3 here, right? Nothing will change, right? So if I do that, then obviously I can also just get rid of 3 here and then reduce it to a single one. Yes?
So you already used 3 lines. Like 1 to connect the 3 batteries and 1 to connect 3 resistors and 1 to connect the 2 lines. So what's the benefit of doing this?
No, I had 3 lines. Right? Now I removed the 3 lines, the return lines here, and I used 1 line.
But you still use 2 lines to connect the 3 resistors and the 3 generators.
No, here, you mean here? These are not lines. This is a node in the circuit. These I can bring them to the same bus bar, and I will screw to the bus bar, screw to the bus bar, screw to the bus bar. So this is a node. This is just a node in the circuit. This is a node in the circuit. These are far away from each other. The load here, these are the generation is very far away from the load, right? So I eliminated 2 cables here, right? But you can come and tell me, okay, but this cable, you put a thick cable here, but this thick cable is not really a thick cable here, because what's going to happen is, from Kirchhoff's current law, what will happen to current at this node? Yeah, so all the currents from this load and this load and this load will be summed up at this node, and then they will flow into this conductor, correct? Right? So if I find a way to make, if this was 1 amp angle 0, 1 amp angle 0, 1 amp angle 0, then what is the current flowing in this conductor? 3 amp angle 0, right? But if I look at how can I utilize the benefit of a 3-phase system, of AC system. If it's a DC system, I don't have a choice. If it's a DC system, I will end up having to put a thick conductor here that is going to carry 3 times the current, right? But now if I forget about the DC system, and now I have transmitting power on AC. If I transmit power on AC and I make these 3 voltage sources 120 degrees apart, so this is 1 voltage source VA, this is 1 voltage source VB, this is 1 voltage source VC. Remember, if these are resistive loads, then the voltages are in phase with the currents, right? So the currents in the loads are also 120 degrees apart, right? So if the currents in the loads are also 120 degrees apart, and they sum up here, so what do I need to do? I need to take this phasor, add it to this phasor, add it to this phasor, right? So I take the A phase, add it to the B phase, add it to the C phase. And what is the sum? 0, right? So they will sum up to 0. That means I can actually theoretically completely remove this. Right? So I can theoretically completely remove this return wire. Right? So I've saved a lot. Instead of 6 conductors, I've used 3 conductors. And that's why when you're driving along at transmission towers, right, you will see 3 conductors strong, or 6 if it's a double circuit. Right? So typically 3 if it's a single circuit tower, and we'll talk more about that, or if you're transmitting 2 sets of 3-phase, you will see 6 conductors. Right? Sometimes you will see a ground connection, but the ground is different. It's a safety issue versus the neutral layer. So neutral connections are not typically used at the transmission level. Typically not used because, who is running the transmission system? Kahrama, not Big Brother, right? So Kahrama is running the transmission system. They are in control of everything, right? If they see an unbalance, so the condition that we used to drop this was what? Was the fact that this is 1 angle 0, this is 1 angle 120, and this was 1 angle 240, right? They're all 120 degrees apart, right? So this is the condition. And so this is 1. So the magnitudes are equal, and the angles are all 120 degrees apart. This is the condition that has to be there for 0 current to flow in this cable, which is what we call the neutral wire, right? So if this condition doesn't exist, what will happen? No? What will happen? They will not sum to 0, right? They just won't sum to 0. I mean, you cannot. They will only sum to 0 if the magnitudes are equal and the currents and the angles are equal, exactly. Otherwise, they will not sum to 0, right? So this is something we cannot control at the distribution level. In this building, for example, 3-phase comes in to the building. Then the engineers that designed the electrical system of the building, they took 1 phase. Here in this room, we are using one of the phases, right? So All the loads here are single phase, right? So the lighting is single phase, the projector is single phase, these are all single phase outlets, etc., right? Is there necessarily a lecture going on in the second room? Not necessarily. The room may be dark, there may be no consumption of load at all, right? So if the engineer designed it such that one of the phases of the three-phase system is coming into this room, the other phase is coming to the other room, is there a balance between the two rooms? Are they seeing the same load? They're not going to be seeing the same load, so there will be an unbalance, right? So in distribution systems, it's very difficult. That's why distribution is it's an art, right? Designing a distribution system, you have to know, okay, who's living here, how they consume power, what time of day they consume power, etc., right? You will study, okay, they will have to know this is a university building. They will have to know approximately how many students. They will have to know, it's the more you know about the load, the better you can distribute the power, right? You don't know too much, you will distribute garbage. Not garbage, but I'm saying like that you will have a significant unbalance and big neutral currents, right? If you have big neutral currents, that's not a good thing, because if you have big neutral current, if there's no neutral current, right, and I connect these with a wire, we said there's no neutral current. So what is the voltage at this node versus the voltage at this node? The same, right? If you have two nodes that are connected, but no current is flowing, it means, current only flows if there's a voltage difference between nodes, right? So if neutral current is flowing, what does it mean? It means that I have a difference in voltage between this node and this node, right? So if there's a difference in voltage between these two nodes, then the neutral point of this three-phase system and the neutral point of this three-phase system are not at the same voltage level. So here, in this outlet, you have what? You have one of the phases, the neutral, and the ground, right? You have the neutral. This neutral, theoretically speaking, I should be able to stick my finger in the neutral socket and not get shocked, right? Theoretically speaking, I should be able to do that. If there is an unbalance in the distribution system, and this unbalance is significant, causing significant current and voltage difference between the neutral points of the generator, which is at 0, and the neutral points of the load, which is, because it's a big unbalance, it's at a certain voltage, you will get electrocuted, right? So, and that's why we also add a ground connection at that point. The ground connection is the reference 0 potential. So now, if there is a difference between the neutral point voltage and the ground connection, current will flow in that, and we will measure that and protect against that, right? So the ground protection is actually a physical ground connection to, actually if you go down, from the cafeteria downstairs in the Batil, you open the door and you go out, there's one small manhole on the floor, and it will say ground rod, right? Look at it, you pay attention to this one, it will say ground rod. They have a big metal rod stuck in the ground, big copper rod stuck in the ground, and the chassis of the electrical equipment, the electrical ground connection is made there. Not all of them, maybe, because the substation that's feeding this building is also down in the garage. So when you go out from the Batil, everything on the right, on the ground floor, is actually, there's a big substation room inside there. There's a big transformer in there. So this transformer is, that's where the neutral point of this transformer is like your generator. It has this neutral point there, and there's a ground connection there. So they have a ground connection there, and hence, if there's a ground connection, which is your reference 0 potential, and you measure the difference between it and the neutral point of your load. If there's a voltage difference, or if there's current flowing, typically, in some cases, we will connect the ground with the neutral. We will talk more about that when we talk about protection here. If current flows, you know that there's a problem here. There's a big unbalance that you didn't design for. Right? So we have protection devices that look at that and protect against it. Okay? So the benefit of three-phase, we see it. Okay, at transmission level, we eliminate three whole cables, which is a big amount of money. At the distribution level, we typically keep the neutral because of this unbalance that it's very difficult to control. At the transmission level, Kahrama is seeing the consumption over Qatar. They have a bigger picture of what's happening. They have control over what's happening in the different loads. So they can supply a different area using two different methods. And if one method is going to cause more unbalance than the other, maybe you supply it with another method, right? So that's that. So in Qatar, we actually have a distribution control center and a transmission control center. So these guys are sitting there looking at things happening in real time all the time. And I will show you a video of something like that. Okay, so we talked about three-phase versus single-phase. Okay, power systems. We said that if I'm putting in the force from the prime mover, and there is no consumption, what's going to happen to the prime mover's rotor? Keep accelerating, right? Hopefully that's clear. So because of that, we have to make sure that the generation matches the loads exactly. So you know the Dell guys. You know when Dell first came out. At that time I was starting to buy computers online. When I went to college, we had the dial-up. We did not have pictures on the internet, right? So it was you dial up and you would download a picture and stuff like that. It was very interesting. But for now, you can go in, configure a computer on Dell, and Dell doesn't actually have stock. Dell has all their suppliers sitting there around the Dell facility. This guy supplies motherboards, hard disk, blah blah blah. You order a computer, and they are the first people that actually created this idea of real-time manufacturing, on-demand manufacturing thing. So you would order, and the suppliers would sell the stuff to Dell in real time. Dell creates the computer and they ship it, right? So they are the first people that created this, and then people started copying it. Yeah. So, but people actually don't know that the power system is the first thing that created that, right? So we have to make sure that generation equals demand all the time. So the people in the control center are sitting there. Okay, you turned on your light. I have to have a generator having enough power to feed this guy's house. No, I'm kidding, but this is really how it works. Otherwise, the frequency changes. Fine, your house is not going to change something, but Qatar Steel. Qatar Steel is a big load, and it's a very funny load because Qatar Steel is melting metal, right? And the way they melt metal is using a short circuit. They create an arc to melt the metal. Right, so this arc, it's a short circuit, right? You're taking a few hundred, all this power. They're connected at 132 kilovolts, but internally they have to bring that voltage down. So they bring that voltage down because they want to create a big arc. Arcs are created when you have high currents, right? We said the arcs are created when fine. You break down the air, but how do you sustain the arc? Arc is current. The arc is nothing but current flow, and the length of the arc is an impedance to the current flow, right? So they bring the two electrodes close to each other, create the arc, and then they start stretching it a little bit, moving it around to melt all the metal that they have, right? So they're creating short circuits intentionally. Really, it's and I was there one time at the distribution center, and these guys were like, Qatar Steel will call them, okay, we're going to turn on, because Qatar Steel turns on and the frequency changes, right? So unless they have enough generation ready to meet that demand, right? So yes, generators, you're on, you're ready, blah blah blah. Qatar Steel is coming on board. So it's actually the biggest machine in the world, right? The electrical power system is the biggest machine in the world. You have to generate because this guy has a load. If you're generating extra, the frequency goes up. You cannot allow that to happen, right? So there are some power stations that will be, for example, supplying a base load. Our power stations that they're on demand to provide peak loads. So the big power stations, actually it's a good point to talk now about these power stations. So there are some smaller power stations that are gas turbine driven. So this is an example of a gas turbine driven, it's called an open cycle or a single cycle power plant, right? Single cycle power plant what happens is the following. You have natural gas coming in, and they are driven by natural gas. So natural gas coming in, natural gas, you combust the natural gas. When you combust the natural gas, what happens to it? You create exhaust steam. You create heat. So this heat is what drives a gas turbine, and this gas turbine shaft is now connected to this generator, which generates the electrical power. And then the excess heat, so the heat was driving the gas turbine, and then there's this air that's driving the gas turbine, still has heat in it, and they just exhaust it. Right? So there are 2-3 of those around Doha. And they are inland, not close to the sea. Right? They are inland, and these are very fast power stations. So these are, they're called peaking power stations. So we have 2 or 3 of those around Doha, and what they do is provide the flexibility, right? These are gas turbines, they're on demand. You can increase the amount of gas coming in, produce more load instantaneously, very quickly, right? So you're not generating steam, you're combusting natural gas, right? There are other types of power plants. So this seems useless, right? This seems very useless to you because I'm giving all this exhaust heat out. I'm not using it's heat. You can utilize it for other processes, for example. Yeah. And that's where our other power plants come into play. Our other power plants are all located around the periphery of Qatar, right? Because they have to be connected to a water source, right? So what happens in this case is you have the same the core of the same core, which is the initial natural gas combustion, and then the gas turbine turning a shaft. Fine, it's turning this shaft, which is eventually connected to the generator. But you have some other stuff as well in there. So the exhaust heat in this case is being used to do what? To heat water, to create steam, and then that steam is then going back. It's going back through here. It's going back through here and feeding a steam turbine. That's connected to the same shaft. Or maybe another shaft and they have 2 generators. It doesn't really matter. It's the idea is you've used that exhaust heat that's coming out to heat steam, to heat water and generate steam. Right? So you use that exhaust heat and then the steam comes back. So the steam goes to the steam turbine, and then after it's used, again, steam, it's like any type of fuel, right? So as soon as you put it in the steam turbine, the temperature of the temperature and pressure of the steam are what drives the turbine, right? At the end, the steam will come out, but it lost its energy. So you collect that steam again, and then you condense it in a condenser, and the condenser is basically you bring in water from the ocean, for example, and you cool it, so the water condenses, so the steam condenses, and then it condenses into water, and then you take that water and go back again and flow through this heat recovery system. You heat that water again, create steam, and so on and so forth, right? But you needed water, you needed cooling water. It's not shown here, but this is what this condenser means. Right? The condenser condenses the steam. How does it condense it? Using cooling. So you can use what is called a cooling tower, or you will bring in water from the ocean, etc., right? So most of the power plants that are in Qatar are operating in a combined cycle, but these take a longer time. It's a bigger process. There's steam in the process, cooling of steam in the process. It's a slower process. So these are mainly called base load power plants. They provide the base load. We know that this building, for example, operates at a base load of a megawatt, for example, right? But when all the students are in the building and the air conditioning load is high, etc., we know there are peaks. And then the night goes down, peaks, and then the night goes down, peaks. So there's a base load. The base load is typically provided by these slower power plants, right? And then the fluctuating loads are typically provided by these faster power plants, right? And the people in the operating room sit down and they have to make sure this is all under control, right? So this is what's happening here. If it's not all under control, then what happens? Then you have some failures and blackouts, right? If the load is too much, for example, the load is too much, meaning Qatar Steel came online, the frequency deviated too much, and there was not enough generation to back that up. Then what happens? The generator's frequency changed, the generator's frequency change, meaning it will fall out of sync. It will not be, it will fall out of synchronism with the network. Fall out. If it falls out, what happens? It's a cascading thing, right? I still have not enough generation because I didn't have, and then I lost more generation. So now I have less generation, so I lose more, and so on and so forth. And that leads to what's called a blackout, or cascading failures that can lead to a blackout. And this can be due to a fault, or a big load, or whatever coming in online, right? Reactive power and capacitors. So inductors, what? Inductors consume reactive power, right? So inductors are, are reactive elements, or are components in the power system that cause the current to lag, right? The voltage. They cause the current to lag the voltage. Right? We don't want this lagging. This lagging versus leading is like, okay, it's like, people riding on a bicycle. You know these bicycles that have several seats? Okay, if you're all riding on the bicycle with several seats and we're all helping each other, we're all straight like this, we're all cycling. Everything is good. What are we doing? We're contributing to real power. We're moving towards our destination. That's real power, right? But then, I don't know, somebody throws a ball at somebody, and then that person had to lean this way, right? But he's still on your bike. He's still on your bike, but he had to lean. So what happens there? He had to lean because that person threw the ball, right? Unless you want him to hurt himself, right? So we have to agree that he has to lean one way. If he leans one way, what is that going to do to your real power transfer goal? Huh?
So reduced.
It's going to reduce the real power transfer goal, right? But his leaning was energy, right? It's energy that he had to do. So his leaning limited his capacity to provide real power. So he is providing some real power by still trying to pedal, as well as he is sort of leaning to duck the ball, right? Duck from the ball. So that's reactive power and real power. So, but if he does this, what's going to happen to everybody else? At some point. Yeah, some people have to lean the other way to balance the bicycle, or otherwise the bicycle will fall down, right? So, and that's what the capacitors do to the system, right? So you put capacitors to do the leaning on the other side, right? So you can sort of bring the power factor back to closer to unity, and hence be transferring real power, right? You want to be transferring real power as much as you can, but this leaning on the sides is causing problems. So we will look at that and how capacitors do that, and you will simulate it, etc., etc. This is mix of generation and stuff. Again, everybody talks about renewable energy. We have a few minutes, so I'm not going to spend too much time on this. I think it's just extra statistics, right? With oil price and gas price, nobody knows, okay? When people predict, okay, gas consumption is going to go down, renewables are going to take the world, but no comment on renewables and gas and oil, etc., etc. I think you can look at that, yeah. We went through power plants. I have another animation of a coal power plant. It's very similar. So this is it's a very. We don't have any coal power plants, obviously, in Qatar. So that's why I didn't talk about it. But again, at the end of the day, you're creating steam, and the steam is running a electrical generator, a turbine which runs a generator. So there will be a boiler room, and there will be, of course, because you're burning coal, there will have to be some extra pollution control measures. And then, of course, there's a power generator that's connected to a steam turbine, and this is the water circulation system for cooling the steam and providing a source of water, right? So this is the whole thing working. Coal comes into the boiler room. What it does is it takes the water, pushes it, and creates steam. This steam goes into a steam turbine. The steam turbine turns the generator. The generator produces electrical power, and of course you have both. This is called a cooling tower. So it's cool. It's helping cool the water. So out of a power plant you would see different smokestacks, right? The cooling tower smokestack is actually good stuff. It's not bad stuff. And then the coal smokestack is the bad stuff, right? So yeah, I think there are lots of pictures on the internet about that, about things like this. Yeah, but yeah, just something to note. Yeah, we went through this again. Nuclear, same thing. At the end of the day, you're taking steam, You're creating steam from water. How do you heat the steam is what people differ on, right? So same thing, take a look at it. I won't talk too much about renewables. They run this. A hydroelectric power plant runs the same way. So you, at the end, you're spinning a turbine that is spinning an electrical generator to produce power. Yeah, you can skim through that. I think maybe many people are taking the 489 course with Dr. Baylog, so he will talk a lot about solar photovoltaics and the materials. I won't talk much about that. At the end of the day, for us, it's a generator. Like we can, like with PowerWorld, with the software that we're going to be using, you are going to model it as a generator. How you control the generator now is the issue, right? Because wind energy and solar energy are intermittent sources, right? So you cannot just say, okay, this generator is 100 kilowatts and keep it there, right? So you will have to put it, show the intermittency of the source. So from a power system perspective, you don't care whether it's coming from wind, coming from solar, coming from a base power plant, coming from a peaking power plant, as long as you know the load curve, right? That's really what matters to us. And because these sources are all peaking, right? So wind is available maybe better at night than in the morning, solar is available in the morning versus at night, then for you to be able to match with the performance of a coal power plant or a gas turbine power plant, what do you need to do? You need to be able to store the energy. Because when the distribution control center wants to dispatch power, right? Dispatch is a fancy word for telling a generator to be ready, right? So when they want to dispatch power, they know that the gas turbine is available. They know that the the combined cycle power plant is available to generate exact amount of power. They know that. So because they know that, when you turn on your load, they know that they can dispatch the power. But when a solar power plant is existing, they have no clue. Okay, maybe the clouds will pass by. If the clouds pass by, then what happens? Can you dispatch power? You cannot, right? So because you cannot, then you cannot use that as a base load. You cannot use renewable energy as a base load because of the intermittency, unless you have storage. You have batteries. You have batteries that balance things out. So when solar is available, you take it and store it. And when it's not available, you use the battery. And hence you have a certain base load that you can create out of the system. But that makes things very expensive, right? So what makes sense is actually, yes, to add a mix of renewables. Yes, add a mix of renewables, but it will be a small percentage of your system. I mean, you cannot. Renewables will not take over the world. People will not go over wars for renewables. That's because of this. Unless we have a magic formula for batteries. I think if there's a magic formula for batteries, then great. Things will be different. Yeah. So for us, it's a source. It doesn't really matter, right? One minute. We'll wrap up. So this is just a picture of the U.S. interconnected power system. So the U.S. is actually divided into 5, I think, three different interconnections. Yeah. So I'll just show you this website. ERCOT. ERCOT is the interconnection responsible for Texas. So Texas is a section by itself. There is a nice video here that you can watch. If you go to the ERCOT website and you go to about ERCOT, please watch this one. We won't go through it, but they tell you more about the U.S. power system. So it's divided up into.
Welcome to ERCOT, which is the short
sections.
name for the Electric Reliability Council of Texas.
I'll just show you the
ERCOT is
picture.
one
Yeah.
of 3 interconnections in the United
So the U.S. is divided into 3 parts. So this system is all interconnected, right? This is all interconnected. This is about 85% of Texas, and then this is all interconnected as well. Texas's consumption is about 68 gigawatts. Right? Peak power consumption. How much is Qatar's consumption? About 6. Right? That's peak in summer. Peak summer consumption about 6. You can go to the QEWC website and they will have the statistics here. So it just tells you the magnitude, right? So Texas by itself is 10 times the power consumption of what we have in Qatar. And it's a big interconnected. Everything is interconnected there. And then these three separate systems are connected using DC links, like we are connected to Saudi Arabia using DC link. So these are all, can you imagine all the generators here in this area, all the generators here are running at the same frequency. So if you stand on the generator shafts, they're all stationary with respect to each other. They're all in synchronism. And here, separately, but not together. Together, the way they interconnect them is with DC links. Yeah. So we'll stop here, watch the video. It's very nice. It gives you more input about what happens in a control room, etc., etc. And then next class we'll start